Good morning, afternoon, or evening. This is my Physics 2211 Lab 2. In this lab, we'll be looking at how we can demonstrate the ability to predict motion with a non-constant force using the method of constantly updating velocity. Here in the top right, we have our Newton's second law, where F net divided by m will give us our change in velocity. So we can calculate a new velocity by taking our old velocity and adding that F net divided by, in this case, the mass of the ball we're dropping, to get that change. And then we can calculate that over and over again. And it doesn't matter that the force is changing, because we're going to keep calculating the force and keep updating our velocity. By observing the falling motion of an object and then using Newton's second law, that's the law right above here, to create two models of motion, we can show how drag force impacts velocity. We'll be calculating our drag force, in this case, by taking a constant b and multiplying it times our velocity squared. And this drag force is always going to be opposite to the velocity we're currently experiencing. So here in the lab, we've got a few constants. Our friction coefficient, which is determined experimentally, the initial mass of the ball, our initial position 0.66 meters off the ground, and initial velocity is 0, because as you can see in the tracker software, I'm just dropping it and it falls. So on the top right here, we have our no drag model. You can see position decreases, and the rate in which it decreases continues to increase. That means it's falling faster and faster, and it continues to accelerate downwards. Meanwhile, with the drag model, it starts similarly, but it kind of evens out, flattens out here. The rate at which it's accelerating downwards is decreasing. That's because the drag is kind of counteracting that velocity and slowing it down. You can see in the same amount of time, about 0.668 seconds, the no drag model manages to reach negative 1.5 meters, while the drag model only gets to about negative 1.3. So in order to calculate those things, we needed to make a few adjustments to the glow script code. We've got mass, position, the air friction value, which we just adjusted until it matched our experimental model correctly, the weight force equation, the drag equation, again using our turbulent drag equation as I showed before, and then F net is factoring in both the weight force and the drag force, and then of course we're updating our velocity and position accordingly, according to Newton's second law, that is. So our final results, you can see experiment in blue, in red we have gravity model, and in yellow we have the drag model. That's of course also affected by gravity, but including drag. They all start out about the same, which is about what would you expect, but as you can see, once the velocity reaches a certain point, once the slope reaches a certain point, the gravity model starts to pull ahead and starts to cover more ground because it doesn't have any drag slowing it down. The drag model and the experimental model stay relatively close. That means we have a decent approximation of what's actually going on. The experiment, however, it wobbles a little bit, you can see here, and kind of gets off track by the end. That is likely due to the blurring I experienced in Tracker. If we perhaps had a camera with a faster frame rate or was filming against a clearer background, we might have been able to prevent that blur. Otherwise, things are relatively close, and it does show how the drag slows down the object. So here we're looking at velocity versus time instead of position versus time. You can see the drag model on the right, as its velocity increases, its velocity, it speeds up, but it's going down, so negative velocity. But it doesn't continue to speed up forever. It starts to smooth out, and if we were doing this over a larger time frame, we would see it smooth out completely. That's its reaching terminal velocity, where the force of the drag is equal to the force of the acceleration caused by gravity times mass, and that would it would smooth out to where velocity is constant. Meanwhile, with a no-drag model, you can see it's constant. Nothing's slowing it down. It's just going to keep accelerating towards infinite negative velocity because there's no slowing down. It's just the acceleration. Now we can talk about here how initial velocity affects terminal velocity. Here we're starting at an initial velocity of -4. We're throwing it downwards, and here the velocity is 0. However, they both smooth out to the same thing, negative 5.33 meters per second downward. Other than that, have a nice day.